Welcome to the first part in this series demonstrating evolved creatures. In this episode, we'll explore the basics using very simple creatures. The creatures are controlled by evolved neural networks using a technique called NEAT. Read more about NEAT in the links in the doobly-doo below. Evolutionary Algorithms is a form of machine learning that takes inspiration from biological evolution such as reproduction, mutation, recombination, and selection. A successful individual is more likely to have offspring than an unsuccessful individual. Over time, successful traits are likely to persist. What we're doing here is also considered reinforcement learning. Wikipedia states that reinforcement learning is an area of machine learning concerned with how software agents ought to take actions in an environment so as to maximize some notion of cumulative reward. Reinforcement learning has recently had an uptick in popularity since researchers have shown how computers can learn to play computer games, drive cars, and control robots totally unsupervised. Unsupervised in this context means without human input or direction. A computer system called AlphaGo recently beat the best human Go player in the world. AlphaGo was purely trained by playing itself over and over again tens of millions of times. The techniques in this episode are massively simpler than what was used in AlphaGo, but it has the benefit of learning extremely fast, allowing us to investigate how evolutionary algorithms work. To be clear, AlphaGo didn't use evolutionary algorithms at all. An evolutionary algorithm requires what's called a fitness function, a way to determine how good a solution is. Think of this as the fitness in Darwinian survival of the fittest. Typically, the fitness is represented by a numerical value. In our case, we're instead considering cost, which is an inverse of fitness. Higher cost is worse, lower cost is better. In this case, the cost is defined as how far the creature is from the target position. Actually, it's the average square distance to the target over time. The faster the creature can arrive at the target and the closer the creature can stay to the target, the lower the cost will be. Get there, stay there, and don't give up the fight. The creatures in this episode have two outputs that control their movement on the game field. The first output controls a force along the x-axis. The second output controls a force along the y-axis. Together they allow the creature to determine the direction to accelerate. The inputs provided to the creature will be varied throughout the different experiments. For a first investigation, let's make the game field simpler and simplify the provided inputs. In this case, we're only providing the position, x and y value of the creature. Those are the only inputs for the creature, two inputs. Note how the initial generation heads off in a random direction. This is partly because each creature is born with a boost in a random direction, but also because the initial random strategy will send the creatures in random directions. There are 150 individual creatures. The one with a green flare is the current leader. The system quickly learns that moving up and to the right is the most effective strategy, so an early winning strategy is simply to go hard and fast up and to the right. But this strategy overshoots the target and a lot of creatures get stuck in the top right corner, which will increase the cost. After some time, the system evolves strategies that tries to stop at the target position and stay there. It takes a few generations, but the creatures eventually become quite good at quickly arriving at the target and staying close to it. Instead of giving the position of the creature as the input, we'll give it delta position to the target, delta x and delta y. This should make the problem substantially simpler to solve. Once the creature hits the target, both inputs should be 0. After a number of generations, we see some interesting behavior. As expected, it becomes quite good at slowing down as it arrives at the target. If you've been wondering about the color of the creatures, each color represents the species the creature belongs to. Individuals of the same species follow similar strategies, their neural networks are similar to each other. The system aims to maintain 15 species for each generation. The The creatures previously didn't know how fast they were going, which makes it hard to find a very good solution. In this example, we provide the creatures with both the delta position and own speed. This allows the creature to slow down when going too fast and speed up when going too slow. From these experiments, we can determine that delta position is better than own position. But when we include speed, it actually takes a bit longer to evolve a good solution. Why might that be? When we have 4 inputs instead of 2 inputs, the search space is much larger and finding a good solution takes longer in a larger search space. But we may assume that including own speed should be able to eventually evolve a better solution, because the creatures should be better at slowing down in time to stop very close to the target. How do we compare these two sets of inputs? How do we figure out which was actually better? Well, one way is to look at how many generations it takes before the best individual hits a specific threshold. For instance, how many generations does it take to get below a cost of 5? Unfortunately, a single run isn't enough to evaluate this, because each run is stochastic or random. So a worse set of inputs could perform better the one time you run the test. Instead, we need to run many tests. Often hundreds are run. So hundreds of runs of hundreds of generations. That quickly becomes time consuming. For now, we won't look at that. We'll just make unsubstantiated assumptions based on our pre-existing expectations. But the graph at the bottom of the screen demonstrates how the fitness of the best individual changes over time, the green line, and how the fitness of the average individual changes over time, the yellow line. So what happens if the creatures has no inputs at all? To make this simpler to solve, we're disabling the initial boost. Since the creature has no inputs that vary at all, it can only come up with static outputs. Note how the UI says that there is one input. That input is a static one because the software requires at least one input. It now becomes a race to come up with the best static force to apply to arrive at the target, but there's no way to slow down or stop. With no inputs, no sophisticated strategies are possible. What if we give it a single input that does vary over time, but not in any way that gives any feedback about the world that the creature finds itself in? In this case, we're providing the creature with the current time, where time 0 is at the beginning of the generation and 1 at the end of the generation. The slider at the top right corner demonstrates the time in the generation. We can predict that the creature, since the environment is non-stochastic, should be able to figure out that it should go up and to the right for a set amount of time, then stop. Note that the evolutionary strategy used, NEAT, isn't perfect. No evolutionary strategy is. Sometimes it gets stuck in a local optima and fails to find the global optima. In those situations, the only solution is to restart evolution completely with a new random generation. How will the creatures handle a set of walls? Can they figure out how to traverse this playing field? Woo-wee! If you think about it, all the previous experiments should have the same results, even though it may take a bit longer to reach the results. With no inputs, the creature still can't evolve a solid strategy, but given time as an input, the creature can work out a set of steps to follow, a schedule if you will, to achieve the goal. When navigating a world with walls, sensors would be the obvious option. In this example, each creature has 4 sensors, sensing in each cardinal direction, up, down, right and left. On the leader creature you can see the 4 sensors as 4 lines. If they're black, that means that they sense nothing along their range. If they're red, it means a wall has been sensed. In a fairly static situation like this, the sensors aren't that useful, but if the target moved, the sensors would be very useful. In later episodes, we'll see things like cars navigate trying to stay on a track. In such situations, sensors are required. What if the target actually moves? All our examples have been to hunt down a stationary target. Chasing a moving target should be harder. Well, if we use the target delta input, following a moving target should be similar to closing in on a stationary target. However, notice how the creatures tend to overshoot the target or approach it extremely slowly. That's because the only information the creatures have are the distance to the target, not how fast the creature is approaching the target. Here's a graphical representation of the neural network that controls the current leader. Inputs enter on the left side and outputs exit on the right side. Remember how the colors represents the species of the creatures. Notice how creatures of the same color behave the same. They tend to move in groups. As the run progresses, the learning rate is decreased. Lower learning rate means that the creatures within a species get more and more similar. This is called exploration versus exploitation. We start by exploring, trying to find a good general solution. Then we move towards exploitation, where we try to optimize that solution. Adding information about how fast the creature is moving allows the creature to better judge when to slow down during an approach to the target. This prevents overshooting and allows the creature to approach at a good clip. Given the increased search space, finding a solution takes longer than before, though a better performing solution should eventually be found. What if we use the speed difference between the creature and the target instead? That should allow the creatures to go where the target will be instead of where it recently was. Indeed, the creatures look more competent. The fitness varies wildly during the run because the environment is much more stochastic now that the target is moving. Let's increase the amount that the target moves and see what happens. As we might expect, the creatures become more clever at predicting where the target is going. Notice how they travel in the same direction as the target as they try to close in on it. That's it for this episode. Did you think of a combination that should have been included in the episode? Let me know in the comments below. In the next episode we'll investigate another type of creature, maybe a car learning to drive, or a two-dimensional quadcopter, a duocopter. Please like, share and subscribe if you enjoyed this video. And as always, thanks for watching.